Welcome to today's Explainer. We're diving straight into what I honestly think is the most dynamic neighborhood in the entire periodic table, the P block. Seriously, just take a look around you right now. The oxygen filling your lungs, the silicon chips powering the device you're using, even those neon signs glowing down the street, you are looking at the P block in action. It's not just a bunch of abstract letters and numbers, it's quite literally the chemistry of life, technology, the environment, and modern industry all rolled into one giant, fascinating package.
So here's our roadmap for today. First, we'll officially welcome you to the P block. 2, we'll cover the rules of the elements. 3, we'll meet the chemical families. 4, we'll see chemistry in the real world. And 5, we'll wrap up with the ultimate exam cheat sheet.
Okay, let's jump right into Section 1, Welcome to the P block, occupying the entire right side of the periodic table. Now, what actually gets an element a VIP ticket into this exclusive P block club? Well, it all comes down to its electronic configuration. For an element to make the cut, its very last electron literally has to enter the p orbital of its outermost or valence shell. The general formula you'll see for this is ns2, np1 through 6. Basically, as you travel across this block from left to right, that p subshell is just gradually filling up, adding 1 to 6 electrons along the way.
Moving on to Section 2, let's establish the rules of the elements and set our baseline.
If you look at groups 13 through 17, watch how the valence electrons behave. They step up perfectly, almost like a staircase, from 3 in group 13 all the way up to 7 in group 17. And the common oxidation states follow a really logical progression too, even though variable oxidation states are super common in this neighborhood. Group 13 usually shows a +3, group 14 shows a +4. But by the time you hit group 17, those are the highly reactive halogens, they are desperately looking for just one more electron to complete their shell, making their most common state a -1.
But, every family has its rule breakers, right? The second period elements, the ones sitting right at the very top of the block, act pretty strangely compared to the rest of their groups. Why is that? Well, it's a combination of their exceptionally small atomic size, their high electronegativity, and the complete absence of d orbitals. This unique combo lets elements like carbon and nitrogen pull off chemical tricks their heavier siblings just can't do, like forming incredibly strong multiple bonds. And speaking of those heavier siblings, as you move down a group, you run into something called the inert pair effect. Heavier elements like thallium or lead actually prefer lower oxidation states. It's almost like their s electrons become lazy or inert and just refuse to participate in bonding. So lead ends up forming a much more stable +2 ion instead of a +4.
All right, let's head into Section 3 and actually meet the chemical families. These are the standout characters of the block. In Group 14, carbon is the absolute star of the show. People often call it the wonder element because it literally forms millions of different compounds. It pulls this off through catenation, its tetravalency, and its knack for forming multiple bonds. But honestly, just look at the wild contrast in its allotropes. On one side, you've got diamond, the hardest natural substance we know of, a total electrical insulator with this incredibly rigid tetrahedral structure. And then, on the exact opposite end of the spectrum, you have graphite. It's soft, it's slippery, it conducts electricity beautifully, and it's built in flat sliding layers. The crazy thing? They are both just pure carbon. It is entirely about how those atoms are arranged. Moving right next door to Group 15, we meet the nitrogen family. Take a deep breath right now. The atmosphere you just pulled into your lungs is massively dominated by nitrogen. We're talking a whopping 78% of it. Nitrogen gas is naturally incredibly stable, basically unreactive at room temperature. And that's because it features this super strong triple bond between its two atoms. It takes a ton of energy to break that bond, but once you do, nitrogen becomes the foundational building block for things like proteins, DNA, and the global fertilizer supply.
Next up, we drop in the group 16, the oxygen family, to look at a true heavyweight compound derived from sulfur. Sulfur all by itself is just this yellow nonmetal, but when we use it to manufacture H2SO4, it creates something legendary. I'm talking about sulfuric acid, which is literally known in the industry as the king of chemicals. We prepare it industrially using the contact process, and it is so absolutely vital to modern manufacturing, from fertilizers to batteries to refining petroleum, that you can actually measure a nation's entire industrial strength just by looking at how much sulfuric acid it produces.
Finally, way over in Group 18, we find the noble gases. These are your chemically inert monoatomic gases sitting pretty with full valence shells, ns2, np6. But wait, there is actually an imposter hiding in the ranks.
Helium officially belongs to group 18 because it acts just like a noble gas, but technically speaking, its electron configuration is simply 1s2. It doesn't even have any p electrons. It really behaves more like an s-block element. But because that valence shell is perfectly full and stable, the periodic table lets it live with the noble gases anyway.
Which brings us to Section 4, Chemistry in the Real World. Let's look at why all of this actually matters outside the lab.
It matters because of monumental industrial breakthroughs like the Haber process. This is exactly how we synthesize ammonia, or NH3. First, we take that incredibly tough triple-bonded nitrogen gas straight from the air and combine it with 3 molecules of hydrogen gas. Then, under immense high pressure and temperature, this reversible reaction yields 2 molecules of ammonia. Why is this such a big deal? Because this single chemical reaction completely sustains the global fertilizer industry. That means the chemistry of the P block is directly responsible for feeding billions of people all over the planet every single day.
But what's truly mind-blowing is realizing that you, yes you, are basically a walking, talking P-block laboratory. Our biological systems are 100% reliant on these exact elements to function. Oxygen is obviously crucial for respiration. Nitrogen is the core building block of our proteins. Phosphorus, from group 15, is literally the backbone of your DNA and the ATP that powers your cells. Sulfur is essential for forming amino acids, and even the group 17 halogens play a massive part. Chlorine is vital for digestion as a key component of your stomach acid, and iodine is strictly required by your thyroid gland just to produce hormones. Literally, without the P block, life as we know it simply wouldn't exist.
All right, let's wrap things up with Section 5. This is the ultimate exam cheat sheet to test your knowledge.
Let's look at a few tricks to rapidly memorize these group members before exam day. Mnemonics are an absolute lifesaver here. For group 13, just remember the incredibly weird nonsense word BalGaNTL. That gives you boron, aluminum, gallium, indium, and thallium. For group 14, just think CSNPB. Carbon, silicon, germanium, tin, and lead. And for the halogens over in group 17, try pronouncing it FClBrI. Fluorine, chlorine, bromine, iodine. Just say those out loud a few times, and those vertical columns will be locked into your brain for sure.
Okay, time for a rapid-fire pop quiz. Question 1. Which group is called the halogens? Is it A, 14, B, 15, C, 16, or D, 17? Well, if you remembered our FClBrI trick from a second ago, you know those highly reactive salt formers make up group 17.
Moving on, pop quiz 2. Which element shows maximum catenation? Is it A, silicon, B, carbon, C, tin, or D, lead? The answer is the wonder element itself, B, carbon.
Pop quiz 3. Which gas protects Earth from harmful UV rays? Is it A, oxygen, B, nitrogen, C, ozone, or D, hydrogen? Now, while oxygen is obviously great for our lungs, it's actually its allotrope C, ozone, or O3 from group 16, that acts as our critical atmospheric shield.
Almost done. Pop quiz 4. Which noble gas is used in balloons? Is it A, neon, B, helium, C, xenon, or D, radon? Think back to our little 1s2 imposter. The extremely lightweight answer here is B, helium.
And here is our final question to wrap up the review. Pop quiz 5. Which acid is called the king of chemicals? Is it A, nitric acid, B, hydrochloric acid, C, sulfuric acid, or D, phosphoric acid? Total industrial dominance belongs to C, sulfuric acid, or H2SO4.
Which brings us right to our conclusion, and I think it's perfectly captured by this quote from our source material. The P block is not merely a chapter of chemistry, it is the chemistry of life, technology, environment, and industry itself. I want to leave you with this thought to chew on. Imagine just how radically different our world would be if even a single P block element, like oxygen, carbon, or silicon, suddenly disappeared tomorrow. Do you think modern civilization would even survive the week? Thanks for exploring with us, and keep questioning the world around you.